Hi, let's continue the lecture on Verilog. Here we'll go with deeper Verilog. And before starting, I want you to, these are things we discussed last class, behavioral modeling, RTL modeling, gate level modeling, etc. So now before starting, I need to know I need to feel, I need to experience why we need Verilog in actuality. So let's see a circuit here. In this circuit, we're given for only 3 gates. Now the question is, what will the change in output C if the input changes from 1 to 0? I give you 2 minutes, or you can pause the video for some time and get the solution. Yeah, I hope you have thought about it and you have got the answer. Most of the analysis, our human nature, or what we have discussed or we have studied in digital electronics, say there's no change in the output. This output remains 0. For example, so how we'll analyze is the initially output was 0, so A will be 1, and 1 is also going to AND gate, and 0 B will be 0, and 0 1 in the AND gate will give Z is equal to 0. Okay, this happens when input is 0. Now what happens if input is 1? Let's see what happens if input is 1. I'm going to try it. Now input is 1, 0 is changed to high or 1. Now this 1 is going to this inverter is going 0 here, and 0 is also going to this AND gate, and it's also going to this AND gate also. So this output of this AND gate is also, this NAND gate becomes 1, and this also 1 is going here. Again C is 0 and 1 in AND gate equals 0. So again 0. So what is, there's no change in the output. Okay, so what is the thing I'm asking you to find out? There's no change in input, so what stuff this is going? But actually, the reality is there is some stuff like this. There is a glitch in the output which we are not able to understand using manual calculation. Why it is happening, we'll see. Now, the main thing is we can see there are 2 paths here. There are 2 paths. One path is this path. Okay, there are only signals going that path. There are only 2 gates. Now, the other path, the signal is traversing 3 gates. You can see this path signal is traversing 3 gates. So there's a delay difference. The difference in first is low. We have a 2 gate delay. In second, there are 3 gate delay. Now, what is happening because of this gate delay? Now, because of the signal is passing here, when signal A is immediately going to the gate and giving the output as C. So initially, this NAND gate was 1 because initially it was 0, this was 1, and yeah, this is 1 and 1, this becomes 0 and 0, C is 0, C is 0 initially. Now when I'm giving 1, what happens? Let's see what happens. Okay, so when I'm giving 1, this immediately becomes 0. Okay, sorry, let's do the reverse. Okay, but the reverse, first it is 1. Okay, so first it is 1, that means it is 1 initially, that means output is 0. Okay, now this 0 is going to C, definitely 0 is 0 because C is faster. In case of 0 is going to NAND gate also. So 1 and 0, this is 1. Okay, now we know this input of the AND gate is 1 and 1 input is 0. Okay, now just want you to see one thing here. When we change the 1 to 0, what happens? This immediately becomes A becomes 1 immediately, right? And this 1 passed to the NAND gate, but before this passed parallel to this AND gate also. Now temporarily we can say before the B is changing, this input of the AND gate is becoming 1 and 1. So immediately C becomes 1 for some time. Then after some time this gate passes the input and this B becomes 0 after some time. Then it becomes again 0. So that means there is some time where C is becoming high because of the gate delay difference. You can see, so that glitches manual calculation we may neglect, but this is very important as a hardware point of view because this glitch can turn on or turn off or something which is unpredictable, and this may cause a hardware catastrophe. So Verilog modeling or modeling simulation or any language is very important because it will give us a practical understanding what is happening in reality. So these things we all discussed, why Verilog is used, because parallel structure, concurrent structure, and origin of Verilog, and why it is different from VHDL, and we have multiplexer. Now let's see a bit deeper what happening in multiplexer. Now we'll discuss. Now we need to increase number of bits of the multiplexer. So what we did, We already discussed these all concepts we discussed last time, but you can remember, you can understand this input thing. We have increased the size of the inputs to 4 bits. You can see 3 to 0. That means we are increasing, instead of 1 bit, using 3 bits. That means 1, 2, 3, 4. This is 0th line, 1, second, third line, 0 to 3. So this A is increased to 4 bits bus. That's the only thing. Rest of the everything remains same, but only the definition is changing. Okay, so by this simple making A and B array, we are making the whole circuit into a bus. Yeah, input is bus and output is also bus. So we have input A 4 bit, input B 4 bit, and one among the A and B is going to the output is also 4 bit. Now we are using here a conditional operator. I'll discuss more about conditional operator in the coming lecture. If select is 1, B is going. If select is not 1, A is going. That's it. Okay, so this we are discussed like last different types of modeling. Okay, this also we discussed. Now, what are the types? What are the things in Verilog which we can use to model the hardware? So one thing is we can use any number of numerical variable or radix in Verilog. For example, in Verilog, this is the way of writing 100, 3-bit 100. The first is size. We have to specify size. How many bits our number is going to take. Then this radix. Then have radix B, H, B for binary, H for hexadecimal. You can see this binary, hexadecimal, H or X, all those things. And value is either 1, high, low, don't care, or high impedance. Okay. So first number of bits, for example 4. I'm representing hexadecimal. So first of H. Now hexadecimal 4 bits is, for example, F. F stands for 1, 1, 1, 1. This is 4 bits. So put it 4. Now we can have different strings also. The strings can be done very long, and there are some special keys or operators like new line, new tab. Like in C, this is new line, this is new tab, and comments. Comments are written like this in Verilog. You can see whatever X, Y, Z you write, this is a comment. And the options commenting is like this: var, star, write whatever things, and then close. Then we have logical operators: logical AND, logical OR, logical NOT, etc. Then we have bitwise operators. This will be acting on a single bit. So bitwise AND, bitwise OR, NOT, XOR, XOR, etc. Now this is an example of illustration how it acts bit by bit. So taking any example, we are writing C not A. So each bit of C is going to A with this bits reverse. So A is 1, so here is 0. 0 becomes 1, 1 becomes 0. And same thing. Here we have binary operator. We are A and B are operated using AND. You can see A and B are combined using the AND operation and resulting in C. Now we have reduction operators. Reduction operator means we have a lot of bits like 1, 0, 1, 0 something. We can combine all these bits and reduce a single bit. For example, I place AND. So all these bits are AND together, and we can see 1, 0, and we have 0, and all those things answer will be 0. So this is called reduction operators. By combining multiple bits or multiple signals using the reduction operators, we can reduce into single bit based on the logical operation AND, OR, XOR, NAND, NOR, XOR, etc. etc. This is a given example. So we have A here. Given A is a 4-bit number 1001, and C called logical ORing, reduction ORing. So you can see if C is all together, we can say 1 is there, so output will be 1 in reduce operator. Now shift operators are right shift and left shift. This is very common in digital for shifting operations. You can take the example here. A is shifted 2 times to the right. Okay, so we know shifting what happens 1 0 1 0. So this is shifted to the right. That means 1 0 become here, and here we have a 0 base here. So this becomes the 2 shifting: logical shifting and arithmetic shifting. We'll discuss this, right? Then concatenation operator. We can concatenate 2 different variables into a single bus. For example, using this statement cat x, we are concatenating A, B, and C. Okay, so we know A is 1 bit, B is 3 bit, and C is 3 bits. So total cat x will be 7 bits. C plus 1 7 bits. And cat y, B and 2 bit binary 1 1 A. A is already 1 bit, then 2 bit, so 3 bit, 3 bit for 3 is also 6 bits. Cat y is 6 bits. Now cat z will be b and a 1 bit. That means b is already 3, so cat z will be 4 bits. So you can calculate the different bits, and also relation operators, greater than, less than, greater than, equal to, less than, equal to, etc. And also output will be 1 or 0. 1 is true or yes, 0 is 0 or false. Okay, equality operator, logical equality, inequality, case inequality, all those things. You have examples here, you can go to the examples, it's very self-explanatory. Conditional operator, we have discussed conditional operator. We have taken an example of a multiplexer here. So here the multiplexer can be easily designed as a selection or conditional operator. So we have two inputs and a select line. Based on the select line, either I will take A or B. So how we write it? Like this. If select is 1, A is going to the output. If select is 0, B is going to the Y. So this is also used in C also. Now arithmetic operators, addition, subtraction, multiplication, division, and mode of, percentage mode of. Now an important thing is to see these two signals. Division. If you write division, it is hardware level. You can see the Verilog compiler is converting this to a simulated output. But hardware level, we don't know whether the device has a predefined hardware synthesis capability or not. So it depends upon the compiler and depends on technology. You should see whether there is a divider within the library or not. But other things, addition, subtraction, multiplications will be there in present compilers. We should see.